Right, so I gave you this distance versus displacement question. Now again, this is hard, okay, and we haven't done area and volume in maths. Now the area and the perimeter of a circle are on the primary school curriculum for maths, but when I haven't actually taught it to you, like, it's fair enough. That's why I hope you got the audio on Schoology. I was trying to give you a bit of a hint on what to do. So anyway, a man walks from A, I have as the start, to B, and he walks by the circular path shown. So he walks on the blue line. What distance did he travel? Okay, so when we were talking the other day about distance, I told you distance was the actual path travelled. Okay, so do you remember I said if I was running, I had myself going into a park and running, it would be if I took like a trundle wheel with me and ran around the entire path. Okay, so when you're trying to calculate the distance, what we want to know is what length is this curved line. Okay, it hinted at the fact that it was circular here, and it is exactly half the circle, so it's a semicircle. Okay, and if you want to figure out the length of the edge of the circle or of any circle, that has a special name, which is the circumference, which I think I mentioned in the voice note on Schoology. And the way you figure out the circumference of a circle is using the formula 2 pi r. Okay? Pi, there's a button on your calculator named pi, which you can just press, or pi is the number 3.14, okay? Depending on which one you want. And then r stands for radius, and 2 is obviously 2. Okay? So, I should say, in maths when we have like 2 pi r all beside each other here with no operation, we should know this from our algebra. These are all little multiplies. Okay, so it's 2 multiplied by pi multiplied by r. So I'm going to use brackets. So 2. Pi is 3.14. And the radius of the circle, so the radius of the circle goes from the center out to the circumference. We talked about the radius recently. Oh, it was when we were talking about circle theorems. Remember we labelled all the parts of a circle. Oh, that was in maths. So hopefully all the maths classes did that and you have an idea of what the radius of a circle is. So the radius in this case is 5. I am just getting my calculator, hang on. Sorry about that. Okay, so I'm typing in 2 multiplied by 3.14 multiplied by 5. And I'm getting 31.4 meters. Okay, so that is the circumference if this man had walked the full, let's try that again. If the man had walked the full circle, that would have been 31.4 meters, okay? But he started at A and ended at B, which was only half the circle. So we're going to need to divide this by 2, which is 15.7 meters. So the distance that he travelled along that curved path was 15.7 meters. Sorry, I'm just going to take this back out. Okay. Okay, so I hope that's okay. There's quite a bit in there. The formula, like I said in that voice note on Schoology, I did hint at, or I may have just told you the formula, but I certainly told you what to look up. This is how you use the formula. So 2 multiplied by pi multiplied by r. And if you use the pi button on your calculator, if anybody, 2 multiplied by pi multiplied by 5, you would have got 30, you get the same, 31.4 rounds to, so either way you would have got the same thing. just with a few more decimal places, but it rounds to 31.4. Okay, what is his displacement from A? Right, so displacement, remembers as the crow flies. So where did he start? Where did he finish? Doesn't matter the path that's taken. All that we care about is start and end. So he started at A and he went in this direction and he ended at B. So the displacement is only 10 meters, okay? It's 5 from A to C and 5 from C to B. And remember that displacement is a vector, which means it's not good enough just to give a magnitude or just to give a size. You also have to give a direction. And if you look up here at the little direction, he moved east. So 10 meters east. Okay, so the distance he actually travelled was 15.7 meters along this curved path. The displacement was 10 meters, and you can't answer a displacement because displacement is a vector. You can't answer that without a direction. So you have to put the direction he moved, which was from A to B, which is in an easterly direction. Okay? We were then asked if the time for his journey is 10 seconds, find the speed. Okay, so speed is a scalar, which means it goes with distance over time. So the distance is 15.7, the time is 10. So So if you do 15.7 divided by 10, you get 1.57 meters per second. And then for part 2, it's the velocity. Velocity is a vector. So remember, you put the vectors with the vectors. So velocity is displacement over time. So displacement is 10. Time is 10. So that comes out to be 1 meter per second. And again, velocity is a vector, so you can't just leave it as 1 meter per second. It's 1 meter per second east. Okay, the velocity will be in the same direction as the displacement, and the displacement is east, so the velocity is east. Okay, so they are your 4 answers. Just let me highlight them. So the distance was 15.7, and to go with that, the speed was 1.57, and then the displacement was 10 meters east, and then to go with that, we have a velocity of 1 meter per second east. Okay, I said to ignore the average words in here, the fact that it keeps saying average. Speed and velocity, they're difficult things to be exact with. How am I trying to explain this? Right, let's say you get in a car and you drive from Dublin to Galway. Okay, let me get a bit of space here. Okay, now these numbers are makey-uppy because I'm literally making them up. So let's say you go from Dublin to Galway in your car, and let's say that is a journey of 200 kilometers, and it takes you 2 hours to do that journey. Okay, and I'm asking you, what's the speed? Okay, so we put the distance. Now I realize my units are wrong. I'm completely aware of that, but let's just go with it for a second. So I put the distance, which is 200, over the time, which is 2, so that is 100, and my distance was kilometers, my time was hours, so it's kilometers per hour, right? So I'm saying the speed that my car was travelling, going from Dublin to Galway, was 100 kilometers per hour. Now if you read that as it's said there, what I'm saying is that at all points on that journey from Dublin to Galway, my car was moving at 100 kilometers per hour. Now, does that make sense? Does it make sense that the car moved at the exact same speed the whole way along the journey from Dublin to Galway? Okay, I hope that you are saying no. that 100's an average speed. Okay, there would definitely have been points on an open motorway where the car was doing, 120, no, what's the speed limit? 120 kilometers per hour. And then there would definitely have been points in the journey where the car was going a lot slower if you meet, like, to be fair, you don't meet a lot of towns going between Dublin and Galway anymore, but even just getting out of Dublin. Okay, so depending on where you live in Dublin, how long it's going to take you to get to the motorway. Depending on what time you get on the motorway, you might meet a little bit of traffic at a junction or whatever, you'll have to slow down. Traffic lights in Dublin, in Galway, you'll have to slow down. Okay, so it is not practical to say that the speed is 100 kilometers per hour, but it is practical to say that the average speed is 100 kilometers per hour. Okay, there will be times in the journey where you were going slower and times in the journey where you were going faster, but it averages out to be 100 kilometers per hour. Okay, so that's where the significance of that average word, it actually doesn't affect your calculations at all. It's more from a practical point of view. Like in a lab, when we, set an object moving down the classroom, we probably could put have it moving at the same speed at all times. We probably could do that. But it's just not practical in the real world. Okay, so this person walking, maybe he tried to maintain his speed all the way through the journey, but again, probably not practical. I know myself when I go out for a walk or a run, like I'm definitely faster in the downhill portions than I am in the uphill portions. I would be faster through the center of my run because at the start I'm warming up and I get like a stitch and I get a little pain here and there. And then towards the end I'm knackered and I'm just trying to get home. So I'm probably at my fastest in that middle part of the run where I've kind of settled in, all the pains and aches are gone and I haven't yet reached tiredness. So it's just not practical to move at a constant, steady speed at all times. Which is why the word average is so important. All right. Doesn't change your calculations, it's more just a thought process. Okay, so we're going to look at distance time graphs, and this should link in nicely to maths. I know that the different maths classes have all kind of chosen to start at different points, but the next thing my class is going to do is speed distance time. And speed distance time links perfectly into this, okay? Literally how you teach it in maths is almost exactly how it's taught in science. The only difference is in science you tend to do experiments around it as opposed to just the maths of it, okay? But it's all very linked. So a distance time graph shows just that, okay? One axis, you can see it here, has the distance on it, and one axis has the time. The time is always on the x-axis, okay? So we did a lot of work, and regardless of which math class you're in, because we did all of this in first year, we did a lot of work when we were doing patterns on graphs, okay? So this horizontal axis here is the x-axis, and the vertical one over here is the y-axis. And when you're doing, in science, if it's anything against time, doesn't matter, distance against time, speed against time, like power against time, it doesn't really matter. Whatever you're plotting against time, the time goes on the x-axis. Okay, it says that there. All right. Okay, so they've done this little graph here. Okay, it's a bit of a funny graph. So it goes up here with a nice slope, and then it flattens out, and then you have another slope, and then it flattens out. Okay, so it will go on to talk about it, but essentially, if you have a sloped straight line, that's where whatever the object is moving at a constant speed. Okay, so this part here, there's a slope to it and it's a straight line, and this part here, there's a slope to it and it's a straight line. At that point, whatever this object is, it doesn't really say what it is, or does it? No, it doesn't. So whatever this object is that's moving is moving at a constant speed during those portions. Now, not necessarily the same speed, and we'll talk about that in a second, but at this portion, constant speed, and at this portion, a different constant speed. Okay? So when you see sloped straight lines, that means constant speed. When you see flat or horizontal straight lines, that is, my dishwasher's finished, that's what the beeping is. So when you have flat or horizontal straight lines, that is, how's the best way to say it? No speed. Basically, it means stationary. Okay, I don't really like no speed, but yeah, essentially that's what it means. Okay, what's after happening? If you look, see this portion here? So that is a 5-second time frame there. And in that 5 seconds, the distance didn't change. So that means that they were 20 meters, let's say 20 meters away from home at 10 seconds, and they were still 20 meters away from home at 15 seconds. They didn't move. They were stationary. Okay? That okay? Oh, crap. Okay, so now I just want to look at the sloped straight lines. Okay? That word there, sloped. Do you remember we can work out the slope? Okay, so I think by eye, you can definitely tell that this line here, this one here, is more sloped than this one here, right? Hopefully you can see that by eye. But let's see, can we remember how to actually calculate the slope? So you make, let's try and use some straight lines. Okay, insert a line. So you make a triangle. You put your line there, insert line, and you put, I'm just going to put it right on here, okay? And then you figure out what the length of this line is, and this one is called your rise, and you figure out what the length of this line is, and this one is called your run. Do you remember this? And the slope is the rise over the run. Yeah? So in this case, the rise, okay, so when you do the rise, you're looking at an up and down direction. So you have to look over here to the y-axis, okay? So for the rise, you're looking at the y-axis. So it starts here, which on the y-axis is 0. And it goes up to here, which on the y-axis is 20. So the difference between 0 and 20 is 20. So the rise is 20. Yeah? Now, this run is actually bang on the line, so it's handy. But for the run, you're looking at the x-axis because the run is horizontal. So it starts here, which is at 0, and it ends here, which is at 10. 0 to 10, that's a run of 10. So 20 divided by 10 is a slope of 2. Yeah? Now, I just want to link this for you, okay? And this is really tricky. Like, I would have 5th and 6th years in physics and still struggle with this concept. So if you get this, it's brilliant, okay? So if I just look at that slope formula, okay, which is rise over run. And I just said that the rise, look, you read off the y-axis. And the run is horizontal, so you read it on the x-axis. Yeah? And the y-axis in this graph is distance. And the x-axis in this graph is time. And what's distance over time equal to? Yeah, we just learned it. Speed. So really, really important idea is that the slope gives us the speed. So when we figure out, which we did above, what the slope was, what we've actually figured out is the speed. Okay? That is a really important concept. When you get the slope of a distance time graph, what you are actually doing is calculating speed. Okay, and this whole process here is why. Okay, we do the slope using rise over run. The rise is the y-axis, the run is the x-axis. The y-axis in this graph contained distance and the x-axis contained time. So then we know that distance over time, because it was back up here. No, that's the vectors. Where is it? Here it is here. Distance over time is speed. Okay, and then by that process, the slope is the speed. Okay, which is a really, really important idea. Oh, I've made a mess of the graph here. Hang on until I tidy this up a bit. Okay, yeah, get rid of that. Okay, right, that's a bit better. Okay, so we just figured out that this line here is a speed, or represents a speed of 2 meters per second. So let's look at this one. The one that I think by eye is steeper or more sloped. So I think we're going to get a bigger answer here. So I'm going to put in my line to make my little triangle. So that goes to there. And then insert a line, and it goes that way. Yeah? So we look at the rise first, which is this one. So it starts here, and remember you're looking over there. So it starts at 20 and it goes up to here. Ooh. Oh God, hang on, I have to clear that now so I can see it. I'll do that with an actual line. Hang on. I was right. Okay, so what have we got here? 2. Oh God, I don't even know what that is. 2, 4, no. So I think halfway is probably 45. Yeah, it's not a very good graph, but let's call it about 44, okay? It's very hard to read. The lines aren't exact. See, 40, there's 1 box, 2 boxes, there's 3 and a bit boxes representing 10. Yeah, so it's not ideal. I reckon that's about halfway there. So let's call it 44. Okay, not perfect, but anyway. So the rise there is 24. Okay, and then down here we'll do the run. So the run starts here, which is at 15, and it finishes here, and I read down, and that's actually 20. So the difference between 15 and 20 is 5. So if we want to get the slope of this part, we do the rise, which is 24, divided by the run, which is 5. So that's 4.8. And remember that the slope is the speed, so that's 4.8 meters per second. Okay, and I expected it to be bigger than the other one, and it is. Okay, so lots and lots there. There are questions here, so we'll have a quick look at these because why not? So let me just tidy up the graph again. Okay. So calculate the total time the student was stationary for. So remember I said stationary was during these flat lines. So that's from 10 to 15. So that's 5 seconds. And then up here it was from 20. Oh God, here we go again. That's there. 21, 22, 23. It's kind of 24. So that's from 20 to 24, so that's 4 seconds. So that is a total of 9 seconds. Okay, again, you really shouldn't have this kind of difficult to read thing on the graph, but anyway, we'll keep going. Calculate his average speed from 15 seconds to 20 seconds. So that's this portion here, which I did, and I got 4.8 meters per second. And what does the steepness of the line tell you about the speed? So I was able to tell you that at the start, the fact that this line here was steeper than this line here, that's moving faster than down here. So just at a glance, you can see that this slope is bigger than this slope, and as a result, this is faster and this is slower. Okay, remember I said they're both constant speeds, but they are different from each other because their slopes are different. Okay, so this here, there are two types of motion. That's what I wrote up above. So objects moving at a constant speed produce a straight line distance time graph showing that they are covering the same distance every second. So that's this one. And objects that are stationary and not moving cause the line and distance to be horizontal. So that's this. Okay, so you probably have that taken down already. And this is what I was going on about up here. Very, 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 very important. And there is homework. I don't know why it is not there, but anyway, I have it on a separate document. So there is a distance time graph for homework. I'm not asking you to draw it. It's drawn as far as I remember, and I'm just asking a couple of questions on it. Okay, so some really, really important stuff there that will help you in both physics and maths. So take the notes down, let me know if there's anything you don't understand, and attempt the homework. It's very similar to this. They give you the graph, and you then have to, just like I did here, you have to answer questions on the graph. All right, so that is due for Friday, isn't it? Yeah, so I will chat to you then.